Welcome to Server Logic Simplified.
Imagine you have critical information, perhaps customer orders or patient records, stored somewhere. What if that single storage location suddenly fails? All that vital data could be lost forever, halting operations and causing significant damage. This scenario highlights a fundamental challenge in building resilient software systems. In distributed systems, data redundancy is maintained primarily through replication. This means creating and storing multiple identical copies of data across different, independent nodes or storage locations. This proactive duplication ensures that if one part of the system experiences a failure, other copies are readily available, preventing data loss and service interruption. The core mechanism behind redundancy is ensuring fault tolerance and high availability. When data is replicated, the system can continue operating even if some components become unreachable or corrupted. Different replication strategies address varying needs for consistency and performance. For instance, synchronous replication guarantees that every copy is updated before a write operation is acknowledged. This provides strong consistency but can introduce latency. Asynchronous replication, on the other hand, acknowledges writes faster but with the trade-off of potential data loss if a primary node fails before its changes propagate. Quorum-based replication balances these by requiring a minimum number of copies to acknowledge a write or read, ensuring a configurable level of consistency and availability. The choice often depends on the application's specific requirements, such as whether strict consistency or high availability is paramount. Practically speaking, implementing data redundancy involves several key steps. First, you define a replication factor, which is the number of identical copies of data to maintain. Common factors are 3 or 5, offering robust protection. Next, you select a replication topology, such as a primary replica setup where one node handles writes and others serve reads, or a multi-primary setup allowing writes to multiple nodes for increased write availability. For very large datasets, sharding is often combined with replication, where data is partitioned into smaller segments, and each segment is then replicated independently. Regular data integrity checks, using checksums or hash comparisons, are also crucial to detect and repair any inconsistencies that might arise across the replicas. Furthermore, taking periodic snapshots and maintaining offsite backups provides an additional layer of protection, acting as a historical redundant copy. When discussing consistency in redundant systems, you often encounter terms like eventual consistency. This model, frequently used in highly available systems, means that all replicas will eventually converge to the same state, but there might be temporary discrepancies. This contrasts with strong consistency, where all replicas are immediately identical. Technologies like Apache Kafka or distributed databases often leverage these concepts. Consensus algorithms, such as Paxos or Raft, are also foundational. They ensure that all nodes in a distributed system agree on a single state, which is critical for maintaining consistency across replicated data, even when failures occur. Understanding these concepts helps in designing systems that appropriately balance the trade-offs between consistency, availability, and partition tolerance, as outlined by the CAP theorem. Ultimately, maintaining data redundancy is about building resilient and dependable distributed systems. By strategically duplicating and distributing your data, you are not just backing it up, you are architecting a system that can gracefully withstand failures, minimize downtime, and protect your most valuable asset, your information. This thoughtful approach ensures business continuity and provides peace of mind, knowing your data remains accessible and intact, no matter what challenges arise in the distributed environment.
If this helps you code smarter, like, subscribe, and stay tuned for more.